Today we have a wonderful session organized on the topic of artificial intelligence and machine learning in manufacturing. We have assembled four wonderful and well-accomplished people in this same space of AI and machine learning, and from a manufacturing point of view, as well as business enterprise point of view. You're going to have an exciting 1.5 hours starting now. So I did a thought exercise a few years back, and everybody was talking about cyber physical systems, and everybody was, it was very popular to talk about CPS being the force behind AI, or AI is going to drive CPS. So I went and then looked into a lot of manufacturing research literature, and this is the word cloud I have come up with at that time. It's about 4 or 5 years old, but still the things have not changed, so I didn't change it. Slide. So one important thing that comes about in this slide is intelligence. Yes, as an important word, intelligent network or intelligent sensing or intelligent systems, they are very prominent. If you drill deeper down into whether sensors networks or the distributed systems or real-time communications, again, intelligence and learning play a big role. Then when I looked into the progression of publications, more from the academic circles, I could see that the number of articles which were using machine learning in their title or AI in the title was progressively was increasing. So this was, I did pick a few journals as sample and then did this particular work. And then I looked into the terminologies that are used. We had about 235 different names for AI and machine learning, or the different techniques. For example, the techniques like artificial neural networks, fuzzy neural network, or k-means or k-median, or linear regression, and all these things. And the slide here shows you the relative frequencies of these particular terminologies. So this is where I felt that in the next few years, at that time, that AI and machine learning are going to be very prominent. Actually, the whole idea of intelligent systems or artificial intelligence was there for a long time. In the 1980s, Yoshikawa from Japan started actually the intelligent manufacturing systems revolution at that time. And Purdue had an intelligent manufacturing systems ERC initiated at that time during the 80s, 1985, with King Sun Fu and Professor Solberg and the other people at that particular time. So the terminology or the word is not new, but the computing facilities and the progress in AI and machine learning have changed things around. And today we see that this is a commonplace, and every industry or every manufacturing industry is trying to embrace AI and machine learning. So in the next 1 hour and a half or a little less than that, we're going to talk about this, and then also after the panelists do their presentations, each one maybe perhaps between 10 to 12 minutes, then we enter into a Q&A session. So without much delay, let me start with the panelists. And the first panelist is Mr. Jimmy Pike. He's a senior vice president and is a senior fellow and the systems architect at Dell. And then he had about 40 plus years of experience, and is a real hands-on person who, according to him, has a PhD in the hard knocks. So I think we're going to learn a lot from him. He has so many patents to his name. And the floor is yours, Jimmy. And we're looking forward to it.
Thank you. I'm delighted to be here and excited to share some thoughts over the next few minutes. This is a real treat for me because technology clearly is one of my passions and one of the areas that I spend a lot of time in. So what I thought would be kind of nice to do is I'm actually going to give you a few minutes of a case study here and actually share a video. I was going to try to share a video and it will not let me. There we go. There we go.
Right.
Thought you could grow a plant in a warehouse instead of a field, without sun, without soil. We're doing it, and we're not only doing it on an experimental level, we're doing it on a commercial level. Today we focus on leafy greens. We believe we can grow anything. Our vision is to build farms in cities all over the world to allow everyone to have access to fresh, great tasting, healthy food all year round. The fact that we can grow plants using 95% less water, 0 pesticides, as much as 390 times the productivity per square foot as a field farmer shows what technology can do. We're able to understand the plants better than anyone ever in the history of farming, and it's by the data. This is why the relationship with Dell Technologies is so valuable. We are collecting all of these data points of what we're giving the plant. What spectrum of light, what nutrients, how do we improve quality, taste, texture? We're using data analytics and becoming better farmers. At the end of the day, it's about how do we deliver a better product to the customer.
This is AeroFarm's baby kale. This is going to be active flavor of kale. The watercress.
Give me the volume is low.
The bok choy is super juicy. This is what I love about AeroFarms is that it's like technology that's allowing people to farm better and smarter, and it makes really delicious food.
The world needs a new paradigm of how we're going to feed this planet. AeroFarms is illustrative of what technology can do to provide more with less.
But farms is because it's such a near and dear thing to all of us. The thing about AeroFarms is it is the epitome of the kind of systems we're going to have to deal with as we look at how we do manufacturing, in this case, manufacturing of food. And as you saw in the video, the idea of being able to grow food in essentially a downtown warehouse in New Jersey and be able to do it at an extraordinarily higher yield, like 390x, at an extraordinarily smaller amount of water, like 95% of the water, is pretty remarkable. In fact, that I think it unleashes the ideas of what manufacturing, not just in material goods can be, but in things like growing, things like food production, and all that can be as we move forward. The thing that makes it kind of interesting is this is an extremely complicated system. So the idea is being able to marry all of the sensor data that you see, the idea of what is the light, what is the humidity, what is the temperature, what are the environmental things that are happening, and then how they can be modified and moved and changed to yield the best results. This is an ideal use of machine learning. In fact, what they've done is they've created these models associated with the way that the plants grow in specific areas, that particular kinds of plants, how they behave and what you do with them. So this is kind of a pictorial of what that system looks like. And it's based on, there's a lot of IoT because like I said, there's an extraordinary amount of sensory information that's done. There is a lot of gathering that is done and modeling back in their case, they create models in the cloud. and then they actually do data mining locally and make modifications. So this is kind of a snapshot of what we're going to see with the systems that are going to be not just in manufacturing as we know them in durable goods, but all over the place. This is a kind of a microcosm of what we're going to see. You know, I look out and I see smart cities, and I see the things associated with smart cities. I look out and I see the automotive industry, which is driving which is headed to have as much as possible autonomous vehicles, and the ability to deal with the data is what's at the bottom of this. This is an extraordinary amount of data. The amount of data coming at us is going to be remarkable, especially if we look at where things are going over the next few years. And the ability to not only process that data, but basically get the information from that data as quickly as possible and at the point where the data is created is going to be paramount to us as we go forward. So that's kind of an idea. It really talks about turning data into intelligence and then using the intelligence to actually create something that drives us forward. Oops, didn't mean to do that. So machine-driven information using machine learning and in this case, a little deep learning. I think that is the future that we're going to have to deal with. And one of the things that I will point out a little bit is most of this is going to be done actually for the development. For example, doing your algorithms, doing your data science, most of it can actually be done locally. It's only where you start putting a large amount of information that you need to understand how to make things scale. But you know, one of the things we've done at Dell is we've created these models which you can get a Dell workstation that has TensorFlow on it, has Jupyter Notebook on it, and most of the data scientist guys can do their work based on that workstation. And then you can scale it as we need to. Now, the other thing that I think we have to be able to do is to scale it very large. So one of the things we do is we have this model where we have this large shared system scheme where we share with our partners and people who are interested techniques and understandings that we've gotten from dealing with many different aspects of machine learning and data learning. And I will tell you this: there is a kind of a crossover between deep learning and HPC. In fact, if I look under the cover, it's extremely hard for me to tell where one stops and one starts. It basically becomes a matter of scale. But those practices that have driven the HPC community for a long time can actually be applied where we see in deep learning and machine learning. And that's one of the things we've done. In fact, at Dell, we actually have this innovation lab where it's a pretty big lab. We invite partners to come test things out and to deal with problems that they're doing, and we'll work with them showing the things that we've learned. And there's an extraordinary large number of publications that we've done as a result of this. So it's an exciting time. There's going to be revolution after revolution as we go forward, especially if you look at where both the software and the accelerator community is headed. And you know, I've been in this business actually for about 45 years. And the one thing I will say is I can't remember when things were changing at the pace they're changing today. So hang on and come see if we can do some things together.
Yeah, thank you, Jimmy. So for a wonderful start for the panel. So we go to the next person. I think yeah, next is Dr. Maja Vukovic. She is a distinguished researcher or distinguished research staff member from IBM and also research manager at IBM Research. And in fact, I have done some good work with her, who had been an inspiration for me in working on crowdsourcing for a while and ubiquitous computing. And then she is a member of the IBM Academy of Technology, and then is also a master inventor and holds more than 130 patents and has received the IEEE Women in Services Computing Award. And then the last but not the least, she got her PhD from University of Cambridge. Maja, without any ado, the floor is yours, and thank you for being a panelist.
Great, thanks, Soundar, and I'm very excited to be here today. As always, sort of working with Soundar is very inspirational to me to explore different applications of the innovative technologies to the manufacturing domain. So today, my point of view is we always talk about AI ML in terms of consuming the data, doing better insights, recommendations, but sort of the way I look at it, another interesting aspect to observe is, so how can AI and ML play also the role in transforming or modernizing the manufacturing processes, right? And here are some of the very high level kind of trends that are out there, right? Obviously data and AI, cloud, there is a strong sort of pull towards cloud. 80% of enterprise workloads, some of which are also in the manufacturing domain, are yet to be modernized and enabled for the cloud. Edge is very much gaining traction. So the interesting question there is like, how can we sort of, with the manufacturing sort of being in the need of modernization, right? How can we do that in a systematic way to ensure the continuity of the processes, right? With over 5 million small and medium business sort of enterprises in this domain, which have some legacy software, legacy scheduling systems, legacy architectures, how can we sort of seamlessly modernize them without sort of disrupting the ongoing processes, right? The removal of these elements may not be really a sustainable solution. So one of the interesting sort of applications of AI and ML that is emerging is really, how do we apply it to these software and machine artifacts, right? When we specifically kind of think about, when I specifically look into the AI innovations that are sort of out there today and how they apply to the manufacturing domain, right? There's a lot of applications of AI in terms of bridging this gap in terms of reasoning with limited data. Often there is data, but it may not be complete. There might be some accuracy. So how can we leverage knowledge graphs and similar techniques to facilitate inferencing and reasoning with limited data? The second one is sort of the one that I'm focusing on today, is what we sort of dubbed as AI for code. So how can we use AI technology such as natural language processing and machine learning, which most of you are probably familiar from applying it to the human language for understanding of the documents and so on. So how can we now apply these same technologies to understanding machines? And these are the machines and systems that have been built dozens of years ago, probably with somewhat limited documentation. They might have evolved. So how can we understand that those systems, extract the business knowledge and evolve these systems, sort of modernize them for the future? And last but not least is the sort of key sort of value of AI is, like, now with AI, while we can create better insights and recommendations, how can we provide the explainability for human practitioners who are sort of absorbing these recommendations and transforming them into actions? How can we gain the trust of the human and explain what is behind the derived recommendations? So when I look at the AI for code, and I touched upon that briefly on the previous chart, like I see sort of three categories and sort of where this relates to manufacturing, right? One is very much around modernization of the system. So understanding that low-level code, being able to sort of abstract it, make it higher level so it's more consumable for the developers. Second area is really around how we apply AI to automate, whether it's to automate code generation, detection of the vulnerabilities in the code. And you can imagine sort of the impact of that when you have a running process in the manufacturing floor. And the third one is around applying natural language processing for code and code artifacts. So being able to abstract and summarize the code to make it more consumable. So there's a lot of opportunities opening up in this domain, as I said, not just limited to the modernization, but overall to the development of systems and their evolution. So to give you an example, some of the legacy systems, and as I alluded, and obviously sort of another challenge is that all these systems, they are typically written in different languages, they coexist, right? But how can we, and I will share with you some of the innovations in terms of how we approach reasoning about legacy systems to be able to modernize them, for example, to microservices based, to make them more consumable and sort of deployable in the cloud and easier to run, right? These applications are, as I said, some of them have millions lines of code been around for dozens of years, maybe even written in some obsolete languages, right? And typically the current approach is that somebody would probably manually rewrite these applications, kind of see through the code and try to understand what is captured there. But there's a sort of where AI comes here is essentially we're exploring use of deep learning and unsupervised clustering to analyze all this code and understand what are the business functions, or if you wish, what are these operations that are represented in the code. So here's in a high level an examples of what we have done with a large application of million lines of code. We were able to essentially analyze the code, understand the relationships between the classes that occur at the runtime, and derive recommended sort of more modular microservices, or essentially break it down into more modular components, which can then enable you more composability and evolution of your processes. And we didn't just use AI to generate these recommendations. We actually are looking into how to use AI and principles of programming language to now actually generate that code so that you are really sort of semi-automatically guiding the developer in the process of evolution. So I'll pause here. I'm very much looking forward to the discussion today, and looking forward to more opportunities of applying AI in manufacturing.
Thank you so much, Maja. The wonderful to listen to you, and the exciting stuff in AI for code. So that has a tremendous amount of applications. So let's go to the next speaker. That is Dr. Paul Witherell.
Okay. I can't share my screen right now.
Can you see the screen?
Yeah.
Yeah. Dr. Paul Witherell, whom I have known for a long time, and with whom we have worked, and then he made me learn some parts of ontology for additive manufacturing in the beginning stages. And he has a very strong background in ontology and manufacturing processes. He's a mechanical engineer in the process engineering division of the systems integration division of NIST. So NIST is under the Department of Commerce, and then predominantly their purpose or their objective is to develop and transfer knowledge to industry. And then he essentially deals with information sciences and manufacturing, and then tries to combine them together. Thank you very much, Paul, for coming today to share your knowledge and then motivate us towards this exciting area. Thank you. Floor is yours.
Thank you, Soundar. Can you see my title slides now?
Yes.
Okay. Not quite sure that that's the one that's coming through in what I'm seeing. I'm seeing a preview. All right, great. Thank you very much for the kind introduction. Sorry, I jumped in a little bit there. I forgot you were going to introduce me before I went to the slides. So good morning, everybody. My name is Paul Witherell. I'm the Associate Program Manager at the Measurement Science for Additive Manufacturing program in the Engineering Lab at NIST. I'm going to come from a little bit different perspective of the previous two speakers, and I'll talk a little bit more of some of this exploration that we've done in the data science, data analytics, machine learning, AI type of realm as it applies to additive manufacturing. So I think it's the next slide. Okay, so a little bit quick background. I'm going to give this a brief snapshot. Additive manufacturing research at NIST is not something that happens just in our manufacturing side of things, just in our engineering lab. It's something that crosses labs. It goes from our information technologies lab to our communication technologies lab. Not quite yet, I guess. Our physical measurements lab, our materials measurements lab, and of course, our engineering lab. So it's a cross-lab effort, and so we have quite a bit of engagement across many different processes, and there are many different measurements, many different types of materials. And so this is something that it's not just a focusing on a type of additive manufacturing, but it creates quite a bit of disparity in the types of data that we're able to generate. And so I wanted to kind of talk a little bit about that. Our facilities at NIST, the facilities engineering lab has the major facilities where we have the capability. We have a couple of production additive manufacturing machines. We have some experimental additive manufacturing machines. And we also have an in-house test build additive manufacturing machine. And so between these machines and between our abilities to measure the parts that we create using surface measurements, using material measurements, we do have quite a bit of data that we are generating. And this kind of leads into a little bit of the program here that I work with, the Measurement Science for Additive Manufacturing program. It's currently organized, and this is kind of a quick snapshot of some of the challenges. So I guess I didn't give a whole big of that background of additive manufacturing, but additive manufacturing, we're talking about 3D printing in essence, a layer by layer process. And the manufacturing aspect of things, we're really focused not necessarily on the printing part, but more on something that's going to be manufactured for industrial use, for end use, something that's going to be deployed someplace. So the work that we've been doing in our Measurement Science for Additive Manufacturing program for the past 7 years at this point, we had a reboot of the program in the past 2 years ago, was focused on looking at how to reduce uncertainties in the additive manufacturing process, going from the beginning of the process to the final part. How do we reduce those uncertainties? How do we get better control over the process so we can improve the quality of the final part and really facilitate the adoption of the manufacturing process overall industry? So it's split up in several different, split up into several different projects within that. In our first boot of the program, and this was back in 2013, what we had done was we had looked at the process of end-to-end digital implementation. We said, okay, where do we start? This is something that is moving into production quickly. So it was still starting getting into the production in 2013, but it wasn't necessarily where it is right now. We were looking for areas of where we could, again, introduce the measurement science that we provide at NIST into this end-to-end transition and find ways that we could maybe improve how parts are made. So at the time when we started in 2013, we were looking at the information flow, the knowledge flow, and we were looking at the opportunities of where in this end-to-end process where we could improve the data structure, where we could improve the representation of different things, where we could improve our understanding of this complex system and how it goes and how it works. So how that evolved over the next 5 years or so is we found a lot of opportunities to create new measurements, to take new measurements, to do new things at both the design side of things, the material side of things, the process side of things, and the parts side of things. And not just as a NIST, obviously the community of additive manufacturing has grown significantly over the past 6 or 7 years. And one of the things that's really talking about our accelerating our growth is the ability to sense things, use sensors, and to generate new sets of data across the process. And so what we've seen is quite a bit of data. We've seen data from the material side of things and the different types of data types here. We've looked at in-process in situ data. This is melt pool monitoring data. Different types of melt pool monitoring data where we start to look at scan strategies as well. Look at data ex situ of the melt pool, where here we're looking at scan tracks and some data that was created by a moving laser. Looking at the material microstructure data, looking at grain size, grain orientation, grain location as well. We're looking at surface roughness. We're looking at the different types of imaging that we can do of surface roughness and different ways that we can characterize the surface of an additive manufacturing part. We're looking at the non-destructive testing of a part using technologies such as ultrasound or XCT, a way to investigate the interior of the part, inside the part, or look for different parts. And this is generating obviously terabytes of data sometimes and creating some of these larger XCT scans. And so the question is, what do we do with all the data? Once it's generated, how is it used? And so this is kind of how we transitioned from our previous program for the first 5 years, where we're looking at, how do we use the systems perspective? How do we frame this end-to-end thing? And now, as we grew over that 5 years, and as the community grew, and as everything grew, what we saw was a lot of data. And what did this data mean? It was for us, particularly the project that I lead, is a lot of opportunity to utilize this data. So we can do things now that maybe we would never have, new opportunities now that perhaps that we never had before. Particularly if we're well organized with the data, how can we feed that back into the process? And so we started by looking at that, by looking how is this traditionally done, what have people done to look at and apply machine learning to additive manufacturing. So the project I lead now is called the Data-Driven Decision Support for Additive Manufacturing. I focus on the data-driven aspect, but I didn't want to get caught in the, are we using machine learning? Are we using data analytics? Are we using AI in the complexity of the interpretations of the different ways of doing things? But the reality is, and particularly in the additive manufacturing realm, which I think is really a good trend setter for what we're seeing in generally in advanced manufacturing, is the amount of data that we're using and that's being generated throughout the value chain is be creating new opportunities for us to increase automation, to learn new things, to improve how our product is made. And so that's kind of where we headed. And I wanted to give a quick snapshot of some of the things, the opportunities that we're taking, and how do we look at this data? How do we investigate this data? What do the opportunities look like? Enhancing the presentation of the data and information to the decision makers, looking at new and existing data to increase its uses and value in the decision making, identifying decision points in the AM value chain where maximum impact value can be achieved through better data analytics, developing best practices in AM analytics support, maximum utility of available data, deploying proof of concept case studies. So what we've done at NIST, and coming from measurement science, where we traditionally look at something, we try to break it down, we try to solve not necessarily an instance of a problem, but we try to solve and understand the problem and look for opportunities where we can really develop standards, develop best practices, and investigate and develop basic technology to help us better understand things. And just the raw data and additive manufacturing has created many opportunities to do this, again, from the idea of how we package the data and how we present it to the end user. New opportunities and things such as, Soundar mentioned he didn't mention, but we had done some previous work in model characterization a few years back, and we were looking at ontologies, and we were looking at how we might characterize how we might characterize physics-based models in additive manufacturing. And that was about 6 years ago at this point. And the landscape has drastically changed, where we've moved from predictive models and model characterization to model composition, to looking at the physics-based with the empirical data, to hybrid modeling, and now more and more folks are looking to transfer learning. And of course, AI and machine learning are tools that are used in doing these types of things. And it's really neat to see how the technology and how we look at the data, analyze the data is creating new opportunities for what we can do in manufacturing. One of the things that we're doing is looking at how do we explore what these decision opportunities are. Where are those touch points where I know which data I have, but how do I introduce that data to the right spot where I can learn from it usefully? If I only have so much data, how can I make that data more useful? If I have useful data, where else can I apply it to? Edge learning opportunities with data. Now we're seeing more and more of things that are being generated. You know, we're generating this knowledge and information, but we're also looking for this real-time control, this real-time processing, this immediate feedback. There's a lot of machine learning AI that's going into that and development into that. Developing best practices in analytics support maximum utility. The concept of VVUQ, and we're seeing under the ASME V&V recently, there was a new subcommittee that was just created on machine learning, and that one was focused on looking at starting to look at the V&V aspects of machine learning and those algorithms, and what does it look like to quantify some of these things. We do some work in the data mining group under PMML, the predictive modeling markup language. How do we represent some of the algorithms that folks are using to analyze the data? We're looking at things, investigating, again, this workflow and what works and doesn't work, and all these new opportunities that these types of data are giving us. It all kind of feeds back into, again, this digital workflow where we have these analytics going from the front to the back. And where do we take opportunities? Where does data best used? And what can we do with it to solve new and emerging problems? So I'm trying to wrap it up quick with, AM data has and is proliferating. So we mentioned when we started this program 7 years ago, it's really taken a turn, and it's I guess mimicked what we've seen in just a general advanced manufacturing. We're seeing more and more sensors, more and more data being generated, more and more opportunities to use this data. System levels approach, that the top-down part I believe is still important. I've tried to show that. And that goes into a little bit, and I think we'll talk about in the panel session, as far as the expert systems versus what we do with just raw data, where the data that's been characterized, that's been typologized, has been ontologized, the information that came from the expert and has been modeled and characterized and made explicit. It's sort of the top-down approach from my perspective, where the data that's just being generated in raw data doesn't care about context. It's just you gave me a sensor, I measured something, this is the measurement of that sensor. And where those things meet, I think is where, a lot of these opportunities people are seeing and really starting to take advantage of. I think there's increased roles to come for the data-driven techniques. I think, again, that's something we'll talk about in the panel session. I'm really looking forward to what the future brings as far as what we're able to do with sensoring and measurement and acting on all this data that's now being generated. So I'll go ahead and stop it right there.
Thank you so much, Paul. I think you took us to the deeper levels or to the trenches of doing
Yeah.
data mining and artificial intelligence. And that's wonderful. And then we go to the next speaker. And thank you for your presentation. And our next presenter is Dr. Joshua Siegel. He is an assistant professor from Michigan State University with the Department of Computer Science and Engineering. He has a lot of things he has created. He is a real hands-on engineer and also has a very strong background. And he was a research scientist at MIT where he got all his degrees. So in mechanical engineering. So he is going to talk one more level deeper than Paul. So it's wonderful. Thank you, Josh, and the floor is yours.
Great, thank you so much for having me. Let me get my screen share up here, and I can put that window off. All right, wonderful. Yeah, so hopefully you can see my slides in full screen right now.
Great.
As was mentioned, my background is mechanical engineering. I've done startups and now I work in computer science. And so this talk tries to blend the perspective of manufacturing engineering, both on the hardware side and on the software side, as well as the business opportunities thereof. I will go through a lot of slides, and if there's a great way to share them, I'm happy to upload them so that you can all review the material after, but I do know that the talk is also being recorded. So what I'll take you through right now is defining a concept called deep technology. We'll get into what is the industrial Internet of Things and what is the Internet of Things more broadly. What is AI? Because I recognize that not everyone here has the same background in AI or manufacturing. Real world examples of what's being done today, and then a little bit of a discussion of how I used AI for manufacturing in one of my companies. So what is deep technology, right? And the reason that I'm introducing this is because AI doesn't exist in a vacuum. We need to get data from somewhere. We need to process it somehow, and we need to apply it to a system. And we do that as part of this broader envelope called deep technology. Deep technology is problem-solving technology that was impossible yesterday, that's hard to build today, and tomorrow has the potential to become so pervasive that it's invisible and so important that we can't live without it. What we are doing with AI in manufacturing checks all of these boxes. We didn't have the compute yesterday. We didn't have the data yesterday. We didn't have the connectivity. But factories are increasingly interconnected. We generate terabytes or even exabytes of data, depending on the scale of the network that we're looking at. Right? And we now, if we're trying to build a new factory, can't afford to do it without making it digital from the start. So deep technology doesn't always start out as deep. It actually evolves over time. And we've got this idea here on the left-hand side. This is called the Kano model. And this is your business school lesson of the day right now. That technology that at one point in time is a delighter, over time actually becomes a basic need. Right? And so you can think of air conditioning. At once, it was expensive, only the elite had it, right? And then people became used to it. And now, for most people, you wouldn't actually go and stay at a hotel without air conditioning because you expect to have it there. The same can be said for AI. The same can be said for IoT. The same can be said for just about any type of technology that we're talking about for AI and ML in manufacturing. Additive manufacturing, by the way, is also another deep technology. If you look at it on the more classic example of the Gartner hype cycle, right, or the adoption cycle, deep tech takes you up to just after the chasm before people have really started to adopt it. And then it becomes high tech and then technology. So that's the context that I want to bring to this discussion, that we are using deep tech to both collect data and to generate AI insights into manufacturing. So like I said, IoT and AI are subsets of this broader class. For those who don't know what IoT is, you might be familiar with M2M, machine-to-machine connectivity. The idea behind M2M is that we use a modem to put anything online, anytime, any place. Typically device-to-device, limited connectivity, one application, one or two parameters of data, not hugely rich information. With deep technology, we can get larger networks, we can build extensible development platforms. Suddenly, cars are talking to houses, are talking to factories, are talking to cities. And that is the idea behind IoT. We have these capabilities that build on M2M so that we can sense to generate data, connect to move data where it's most useful, infer to turn information into insight, and then act to close that loop so that we can operationalize the data and make our factories better, make our processes better. And that's driven by advances in low-cost sensing, scalable processing, and pervasive connectivity. So the way that we define IoT in this context is devices and services that connect to one another intelligently and that sense, infer, and act. It's a design language for the future. The industrial IoT is the IoT as it applies to industry, simply enough. Right? And the way that we're doing that today, for those who aren't intimately familiar with manufacturing processes, is primarily supply chain and logistics. We can use RFID tags. We can use really low-cost radios that we stick onto devices. They're literally stickers that cost about 5 cents, right? And we interrogate them with a reader. The reader sends out a radio wave. The tag picks up that energy, modulates it, and responds with an ID and says, hey, here I am. And if I look that up, then I can figure out what device was where, when. Turns out we can also use RFID as a sensor for IoT or IIoT. We can put the environment in circuit with the antenna, and for 5 cents or less, we can have a disposable sensor that can do some pretty incredible things in a manufacturing context. So these are examples of work that the Auto ID lab at MIT did while I was there. On the left-hand side, you can see an RFID tag on a glass of beer. And this was actually the result of a bet trying to figure out if we could determine how full a glass was using radio waves. Turns out liquid attenuates the signal. If you put the RFID tag on a glass, your server can know when your glass needs a refill, right? And if you can pitch that the right way, you can get your PI to pay for beer for you in your lab. On the right-hand side, we did some cold chain projects. These are RFID tags on a shape memory polymer on a metal backplane. And based on that, you can determine the temperature of something in real time for 10 cents. Disposable, batteryless, pretty much infinite life. Up here, you can see a sputtering mask where we were able to vapor deposit metal onto a glass jar. We filled that with salt water so that we could tune the freeze temperature. We put an RFID IC on there, right? And if that jar froze, the antenna would break, you wouldn't be able to pick it up, and you'd know that your vaccine got frozen in transit and was no longer useful. And over here, these are RFID tags adhered to concrete, so you can determine if there are cracks in the structure. So that's a little bit of industrial IoT and sort of dipping our toes in to figure out how we can generate data at low cost and pervasively. What's AI? I think most people here understand already. AI algorithms distill information into insight, and we use that insight to inform people and processes. If you don't know Charles Steinmetz, the Wizard of Schenectady, I recommend you look up his story. But the idea is you can start with a lot of information and it's not that valuable. What you're really looking for is the little bit of data that gives you exactly what you need, right? And you need that right information in the right format. If you've got a parking meter or a washing machine, you need coins, not dollar bills. The same thing is true for your data. And you need it in the right order, right? If you are someone buying a car, you need things assembled properly. If you're a crash test engineer, they might be more valuable if they're actually disassembled. Within AI, there are different types of algorithms and insight areas, right? There's clustering, can I group data together? Regression, how do I relate an input to an output? Classification, how do I assign a label to this information? Is it A or B? And then the insight areas are descriptive, what happened? Diagnostic, why did it happen? Predictive, what's going to happen next? And prescriptive, what the heck do I do about it? And that last one is really what we're building up to now in manufacturing. We can tell what happened. We can tell generally why it happened. But what we do within an organization, that's the difficult part that we're struggling with right now. Within AI, there are two classes that we typically discuss. It's a little bit more nuanced than that, but if you're looking at a high level, you've got machine learning, right? And machine learning says, I know something about this system. I will therefore use my process knowledge to understand what's going on. And I'll use that to codify rules about good versus bad. Deep learning, you just collect a lot of information. The machine figures out what's going on. Sometimes it's right, sometimes it's wrong. I think we'll talk about that later. My takeaway here is deep learning is not new. It's not always the right choice, and we can talk about why, but it can find invalid relationships between data. IIoT and AI underpin Industry 4.0. You've probably heard this term before. That's a lot of what we're talking about today, right? How does it do that? Well, we can use analytics to improve quality, so we can make the product better, but we can also improve consumer product fit. We can make better products, so we can make things that people actually want and really need. We can generate what we call Pareto data. This is a term that I've coined and that I'm using in my lab. Having worked with a lot of companies and consulted with them on how to implement digital transformation, a lot of people are stuck on the idea that they need a $10,000 sensor and perfect data for something to work right. The reality is you can get $100 sensors, and that yields a far more valuable insight for most industries. So here we've got a Shoreline benchtop mill, just a basic manufacturing tool, can deal with wood, aluminum, light cuts, and steel. We've got a Raspberry Pi and an Arduino with an accelerometer. And based on that, we can determine machine health. Now, just because we're using a small machine doesn't mean that the techniques don't apply to larger equipment. You literally could duct tape an accelerometer onto a mill in a factory and get really good insight. And the way that that looks is like this. So this is, on the left-hand side, a waterfall chart of FFTs, so fast Fourier transforms of data showing what's going on in manufacturing equipment. If you look at the peaks of the frequency, you can figure out, for example, spindle speed and belt speed. You know if there's a difference between the two speeds, that you've got slip. You can characterize that inefficiency. You can look at your cutting flute. If that intensity spikes over time, your tool's wearing down. You can use cameras to take pictures of cutting equipment. You can do this in process with high-speed cameras to figure out that there are issues with wear. You can even look at embodied energy. So look at the energy of a cutting tool, look at the material removal rate, and figure out what alloy it is. So in-process supervision can tell you what you're working on. So all of this allows industry to work towards individualized production, right? It used to be craftspeople, bespoke goods, then it became mass production. We're looping back on ourselves here. And the way that we enable that is by using IIoT for safe remote control. We use semantic web, so machines can talk to each other. And that way we can have elastic factories. So it's not my factory or your factory, it's the aggregate of our factories seeking bids to figure out who can make which item at what price in which region. That's actually, by the way, how companies like Zara work. They distribute their design and manufacturing globally. We can also detect faults in components as we manufacture them. So we heard a little bit about additive manufacturing. This is a project that I did using flash thermography for additive manufacturing. Basically, super bright camera flash, and then a heat camera, thermal camera, that studies the cooling rate over time. And using AI, you can figure out, are there delamination to subsurface? Right? So it's like X-ray, except a lot cheaper. And you can do this if you're making one part. All of this works to uncover hidden factories unnoticed by sparse sensing. So again, this idea of Pareto data from 100 things at $100 a pop. You can figure out, where do you get faults? Where do you need to do rework? What's going wrong? And AI also supports infrastructure within the factory itself. So things like self-driving capabilities that are hard to prove in the wild. It turns out the factory is the perfect environment, and we can actually build vehicles that not only drive themselves in a factory, but learn which route they should take to be more efficient and to improve quality and throughput. I want to leave you with the idea that It's far easier to build AI solutions than you think. You don't need a big team. You don't necessarily need trillions of samples of data. These are examples that my own company did. And this was like Shazam for cars. The company was called Data Driven. And you recorded audio of your vehicle and it told you what type of car it was, what's going on with the engine, when do you need to change your oil, when do you need to inflate your tires. Right? And I was able to do this, one guy with an iPhone and a Zipcar membership, collect the data, develop the analytics, and then see what comes out from it. And all of this comes back to that idea of understanding physics, like we talked about deep learning versus machine learning. I don't love deep learning for industry. I think it's really easy to find overfit. In this case, we used machine learning. We used data available on a phone, in this case, GPS to get linear velocity, accelerometers to figure out the rotational velocity of the wheel. From that, you can figure out the tire radius, and that tells you tire pressure. Right? So simple things where you just need to take a step back and think about what is it that I'm measuring. So a lot of information. Like I said, I'll make these slides available. What did we cover? We redefined the Internet of Things, devices and services that connect to one another intelligently and that sense, infer, and act. We talked about IIoT is adding large scale, logistics, and manufacturing. We learned that AI turns information into insight. We learned that the factory of the future will use both of these elements along with other elements of deep tech to make the right product and to make the product right. And we learned that it doesn't have to be hard or expensive to implement AI and IoT in industrial settings. So thank you for your time and attention.
Yeah, thank you so much, Josh. It was a beautiful presentation. You took us from the ground level to the higher level, and you basically combined the academics with the industry. That was beautiful. Thank you so much for being on this panel. So this is me for those who don't like for the audience. My name is Soundar Kumara. I'm moderating this session, and I thank all the speakers for giving their perspectives, which I think together is really very comprehensive. We didn't plan for it this way, but it worked out very, very beautifully, coming from the top level of how things are, even your food that is most important to you is made, or how AI and ML can be used to make it, to making sure that your car is working very well. I think that progression was very well seen in the knitting of all these four talks. When I started sensing between 1989 and 95 and 2000, I was dealing with raw data and then studying the complexity and trying to understand both the physics as well as the nonlinearity in the data. From there to today, in terms of the theoretical work, it has progressed a lot. In terms of applied, also it has progressed a lot. But still, there are lots of questions we can ask. So I think this is the time for Q&A. I had a few questions which I already sent to the panelists to think through and then to give their opinion about them. So we start with these questions, and please you go to the Q&A panel on Zoom, and then you can post your questions so we can take those too. And again, thanks to all the panelists for these wonderful, inspiring discussions. So the first question is, what do you think should be the most important applied problems we should be tackling in manufacturing? So we can start from the way we started the discussion, Jimmy, Mr. Jimmy Pike.
Sure, great question. One of the things I think we're all struggling with is standard formats for interchanging data and thereby interchanging knowledge. I know that there are a lot of people who are looking at this, and everything that we're doing today is built on data for the most part. I really enjoyed the last presentation, especially the idea that we over-index on deep learning. But the idea for being able to create trained models and to be able to allow those trained models to be used by other people and have data exchanges that occur, that's one of the most important things I think we could do, because it is what's going to drive a lot of the next set of revolutions in manufacturing.
What do you think, Maya?
So I think about a couple of domains. I think sort of with the recent sort of changes in the climate, I think one of the sort of domains to be explored, and I'm sort of seeing the rise of these kind of challenges is, for example, enabling reasoning about manufacturing processes and kind of what is the optimal sort of what would be the kind of like examples of carbon accounting tools for different manufacturing processes, how to build decision making and use case kind of what if scenarios when it comes to introduction of the expert systems. That's one domain. The second domain, sort of still from my initial introduction, is a lot of the manufacturing machines may be becoming obsolete. So how are we going to address that and make them sort of relevant and continue sort of building upon them and extracting the information and knowledge from them. So those two areas from my perspective.
Wonderful. So Paul, and you have anything to
I mean, I guess when I first saw it, I thought differently than how Jimmy responded, but I appreciate that response. And Maya too. I guess when I see the word applied problems there, I put it back in the context of what my presentation was about. And I don't feel like there's kind of a one size fits all type of approach that we can take. So if we're talking about applying the problems of manufacturing, and if the goal is to how do we manufacture better, I think interoperability and communication, being able to use the data is important. But then you have to ask yourself the question is, what is the problem that we're trying to solve? What are we applying it to? And I think that very much might depend on what is your maximum impact, what is the maximum value, how do you get maximum utility out of your manufacturing process, and how do we best understand where those opportunities are. And so I guess it depends on what type of approach you're taking to the application. And so those are my thoughts. I think it's not one size fits all. If you're talking about applying to a manufacturing process, I think it's important to understand where the opportunities are, where those decision points are, and where there's actually potential for improvement, as opposed to solving problems that aren't necessarily there.
Wonderful. Josh, you want to add anything?
Sure. So I think there are two challenges, and I don't know if they really fall into the view of applied problems, but I'm going to answer them anyway. And I would say the first is an issue of knowledge, which is companies don't know the data that can exist, and they don't know the problems that they have. If they can quantify the problems, if they can find the hidden factories, and if they can figure out the resources at their disposal to collect data, I think that manufacturing will be far better off. In working with companies trying to go through digital transformation, they all ask for, how do we implement this technology? And then you say, why are you doing this? And they can't answer that question. So understanding what they're trying to do and the tools at their disposal is really important. I said there were two answers, the first being the knowledge, the second is culture. I think you need to have the right workers, you need to have the right mindset. You need people willing to both trust AI and to question AI and to understand what it can do and the limitations of anything that you develop. I also think that there is this perfection mindset that a lot of people strive to get the right system done and time and cost to be damned. And in reality, sometimes getting something out the door and getting first mover advantage and getting data collection really is what companies should be doing. So getting past that design paralysis is another big opportunity.
Wonderful. I think for the next question is a similar one, but in terms of what are the research problems? So I'm not going to ask A, B, C, D, but you guys can chime in and then talk. What do you think are the research problems?
So, sorry, did I cut anyone off?
No,
Go
I
for
think this is a free form for four of you.
Sure. So I think manufacturing has largely been commoditized, and what differentiates facilities now is, again, making the right product and making the product right. And so in terms of the research problems that we should be tackling, it's again a two-pronged approach of, can we ensure that our process does what we expect it to do consistently, repeatably, at a low cost, at a high throughput? And if we can do that, can we then help companies who come to us for contract manufacturing to better understand their customers and make sure that we're delivering not what they're asking for, but what they need, because they're often incongruous ideas.
Great. Any other
I-
comment?
Yeah, I guess I agree. It's I think Josh made a couple of good points where it's, you know, it's understanding your process, and I think that point was also made early on about the over dependency on deep learning, understanding what those decision points are and touch points are, and what the implications are when you start messing around with them and playing with them. So I think the first thing you need to do is understand your process, understand the controls, and understand where improvements are potential, and then also be able to identify how you can leverage what you have available to you. And so again, it's that top down and that bottom up approach. One, you want to have that expert knowledge in there, but two, you want to utilize your new capabilities with sensing as much as possible and machine learning and with AI. And there's that meeting, I think, is where there's a lot of opportunities.
I think one of the sort of maybe perhaps more of an IT or technology challenges building up on what Paul was talking about is I believe data management, right? With the vast amount of data potentially now being unleashed from the processes and sensors, how can you effectively curate them, close the gaps in any sort of missing knowledge and enable sort of effective reasoning?
I would have to say that I agree with that. That, in my opinion, is probably the most difficult problem of all things to solve, is the curation of data and the idea that you can do something that actually validates your data and understand what it really means. When I'm faced with, my experience has been when I'm faced with machine learning or deep learning problems, 90% of the time goes into the preparation and the curation of the data. And especially when it comes to training models, does your model have some sort of bias? Are there unexpected consequences? Being able to automate that and to find quick and easy ways for us to understand how to really find those problems in model sets is extremely important for deep learning. It does also show as Josh pointed out, the idea that we can be over dependent on deep learning, and I think sometimes we do that.
Wonderful. I think the point that comes across here on the data point of view actually takes us naturally to the next question, which is an important question. Maybe we go to this. This is the next question that relates to all the data you talked about, all the discussion we had just now, and also it relates to the question from an audience. So Michael asked a question about like the whole technology is like a black box, and then people on the shop floor don't want to accept this and then start using it. So there are two aspects to it. One is industry is not willing to share the data. Number two, a person or people working on the shop floor not willing to accept what you generated out of the data. So how do you handle this dissonance between the unwillingness to share the data, unwillingness to accept the model, and all this new and greatest and latest technologies? What do you think? This is an important question.
Maybe I can start. Sort of two things come to my mind. One is more pragmatic. The first one is, I believe it actually for both, it's the question of incentives, right? In particular, when it comes to knowledge sharing. So for the second one, it would be really how do you involve the practitioners in the process of not just data collection, but also validating the results. But I think from the point of perspective of your first question, I think we should look into some of the successful ecosystems, for example, although they're more centered around consumer applications and data, but there are many good examples out there where data is being shared, APIs are being available so that you can sort of create new value on top of that. But more specifically to the point about how there is a reluctancy of opening up the data streams. I think sort of federated learning starts to offer sort of at least a pragmatic approach where you can do a partial data on-prem, right? And also handle kind of deal with the differential privacy if there is an issue on how do you expose your data sets to others and potentially kind of resolve any competitive concerns. So I think in a nutshell, incentives and looking into federative learning can address some of these aspects.
To kind of build on that, I think, and I'm sorry, I'm looking at a black screen now. I think Google failed me someplace in there because I don't have any video feed from this, but I don't want to lose the audio feed, so I'm just going to leave it.
So you want to share? Do you want to share the screen?
Oh no, I'm saying I can't see your screen. Oh, were you sharing the questions still? I thought you had been sharing the questions.
Yeah. I'm on question 4.
Yeah, I can't see that anymore. It's on my end, I believe. But to respond to the question about the federation and how do you utilize the data and this disparate data systems, I again put that back into some of the interesting opportunities and how we understand the data and understand what the problem is. Where I think there's utility to be learned from data at different levels of granularity, and I think there's some interesting challenges in. And can you provide information, whether you're using some type of vector, whether you're using some type of aggregate, where you can share enough information without exposing all of your data, while at the same time, share useful information to solve a particular problem. And I don't think that that's something that's really been studied a lot, but I think there's interesting areas of opportunity there, particularly, it kind of requires that common understanding of what your problem, what your context is. But I think if you can start to achieve that in particular domains, it opens up new opportunities for sharing your experience and sharing your data without necessarily exposing everything.
Okay, great. Now can you see the screen?
No, like I said, I'm afraid I'm going to drop off if I try to fix it. So
Okay.
It's just my computer.
Any other response for this question? I think there are 3 things that are interwoven along with Michael's question. One is people unwilling to share data. The other one is the people are not willing to believe the model. I think some of these questions did address them. So,
Soundar,
yeah.
If I might jump in for 1 second, I would say generally a rising tide raises all boats, and most C-suite executives will get that if you can paint the right financial picture for them. It's really difficult to quantify the value in AI, but it's worth doing. That's how you get buy-in across organizations. That's how you create partnership opportunities. I think that there's another latent challenge. It's not just, do we get companies to share data and do we trust the model? There's also the issue of, would you trust the data set that someone else shares? And if you can't control the experiment, if you can't see the provenance, who's handled it, how has it been pre-processed, you don't necessarily know that you can trust someone else's input data. There's an IoT project I'm working on right now, and all of that is about making sure that you understand the custody chain of who handles information, right? There are 2 attitudes that companies either struggle with or thrive from, and it's this idea of not invented here, we can't use it, or proudly found elsewhere, we celebrate other people's victories and build on them. And today, too many companies really focus on not invented here. And again, it comes down to culture of, can we get people to celebrate proudly found elsewhere if they can trust that it was done right? And that's where provenance comes in.
Wonderful. I think I'm going to go to question 3 because the flow. So today, most of the times when you say AI, it is deep learning. That's is there life after deep learning in manufacturing?
So I think I'll take this one maybe. I think definitely deep learning is sort of takes the prime spot in any industry nowadays. I think pervasively it gets often sort of people when they talk about AI and ML, right, without getting here into being picky, right? They often sort of refer to deep learning. But I believe actually manufacturing is a very fertile ground and a perfect domain for what I believe is coming next in AI, which is neurosymbolic reasoning, right? A hybrid model where sort of knowledge bases and symbolic techniques are going to be coming together, and AI reasoning will be coming together with the sort of deep learning models, right? To help drive the explainability and sort of to augment the human intelligence in the processes. So that's my take on this.
Wonderful.
I agree. Add to that graph analytics and the ability to use graphs to help understand and map relationships. I think those two things together are absolutely going to change things as we know them. I see the same problem that people refer to. I actually don't like the term artificial intelligence because it has so many convoluted ideas that are associated with it. But one thing's for sure, we've been doing this for a long time. Machine learning started out being algorithmically driven, and deep learning was kind of a subset of machine learning that was based on data. Why? Because the internet gave us this extraordinary amount of tagged data. In fact, you could probably find more photos of a cat on the internet than any other thing on the planet. And that really did kind of lead us to this whole model about it's all about the data. You get the data and you do things, and that's correct. But it doesn't solve the problem of is the data correct? And it doesn't solve the problem, is deep learning appropriate for all problems, because we do over-index in that. So these are the things we're going to have to challenge. Now, is there life after deep learning? You bet there is. And I can't wait to see whatever it is.
I agree with everything that Jimmy just said. And I guess the one thing that he did say was, is deep learning going to solve all the problems? And obviously not. Obviously, there's lots of ways that we can approach how we can better educate or better characterize or better inform what's going on in any deep learning algorithms. But at the same time, I think there is a nice place for some of those things, and I think it's still people are still trying to understand what might work best for deep learning, what might not work not as best. But when I think of some of the raw data that comes out of the additive manufacturing processes, where it's not necessarily making a decision with the data, but just trying to understand the data, or not even to understand it, just try to label it or characterize it. I think there are applications where the deep learning approach still does make a lot of sense. And so I think it's better, understanding where it makes sense to apply it as much as possible and drive new things and understand what its limitations and faults are is important.
Wonderful. So I think we're in the appropriate point here. What should we be educating our students on, and also our manufacturing professionals? Because this also goes back to the earlier question. People on the shop floor don't trust these models. They're all black box. So what do we do? So what is your take on this?
We've kind of done this to ourselves. Certainly, I'm predominantly in the IT side of the world, and we like to create these extraordinarily difficult descriptions of things that really describe to the T what we're doing. And I think that creates a little bit of level of, let's call it, I don't want to call it distrust, but at least lack of understanding. If you look at what it's at the base of deep learning, machine learning, and artificial intelligence, it's really pretty simple. Machine learning and deep learning I see this, and by see this, I mean I recognize a pattern. Now we as humans, we look out and we see things, and then we generally see things in 3 dimensions. With machine learning, deep learning, you can see things in hundreds of dimensions, something that a person can't comprehend. So understanding that it's recognizing the pattern or recognizing the image, and there's a good reason why you recognize the image. And then of course, AI on top of that is see this, then do this. If we could come up with practical ways to help people understand what's behind this, there is an extraordinary amount of high caliber math that really drives all this stuff, especially when you get neural networks, et cetera, things like that. But the basic concepts behind them are pretty simple, and we should focus on the practical, simple way of explaining how these things work. And I think that would create help in our whole ability to adapt these things.
Any other?
I guess I kind of disagree a little bit there. Coming from NIST, I work with industry and work with academics. On the academic side, sometimes I feel like people are very, how do you make the algorithm a little bit better? But then, what are you validating against? Is your algorithm a little bit better? Or did your validation criteria change? And so those types of things where the application and the applied, where you start to think of, how good does it need to be in order to be useful applied, is often lost, I think, a lot on the academic side of things. And it really kind of, it would be great to give them more on the educational side of things, the academic side of things, more of that type of perspective to understand, how good is needed to be applied, what real world validation criteria might look like a little bit better. But I think coming from the professionals, the folks that are going to use this in manufacturing, folks that are going to use things like machine learning and deep learning and AI. I think of maybe what we're doing with smart cars and what we're looking for full automation. When you see people willing to take up and drive and people looking forward to something like a full self-driving Tesla, when you give them the Tesla, you're not going to have to educate them on exactly how everything in that Tesla works. Sometimes people are going to be willing to just accept it as something that works. So I think there's at some point there's going to be an acceptance necessary that this has been proven out multiple times and able to work. I agree there's some education that's needed, but I think if too much education, it can quickly people can gloss over it. So I think as things start to be deployed and you start to realize what you can actually achieve, I think that will start to lead to a little bit more acceptance of some of these black boxes as well.
Wonderful.
Yeah, I would just say not everyone needs to know everything. And to Paul's point, some people should be trained in how a Tesla drives itself or how a Cadillac with Super Cruise drives itself. And other people should trust that there are smart people doing the right thing and doing the right testing. For the people who are developing those systems, I think the most important thing to cultivate, and certainly where I've seen things going with the boot camps that I run and the exec ed programs, is teaching people to be faithful to a problem, not a discipline. And as academics, that's something that we really struggle with, which is we've got our silo, this is our domain, and don't you dare touch my domain and I won't touch yours. But the reality is, it's not only the world that's flat, it's these pools of knowledge that really are becoming increasingly important to understand in aggregate, because that's how you get the benefit, right? It's the knowledge at the interstitial regions between domains.
Do you have any comments? Maya?
No comments for me.
So let's see, more than this. So there is a question from the audience, which I think is relevant. Maya touched upon this in her presentation, like about the SMEs and the 5.2 million. So in fact, this person from the audience asked the question, 99% of the SMEs are 99% of manufacturing organizations are SMEs, small and medium enterprises. How are you going to take them? Because most of them have legacy missions. How do you make them go into this new AI ML driven kind of economy? What is your take on that? That was the question from the audience.
I think it kind of goes back to the last point where, and Josh did make a good point too, where there are people that you might want to educate a little bit about things, that want to know about it a little bit more. But I think in small and medium enterprises, it always comes down to, the bottom line. Their objective and their goal is to make money. So if you're able to prove out a black box and demonstrate that their black box is going to increase the value of what they're able to produce, then I think that will you will see adoption there. I was actually just reading something the other day about the amount of pre-orders that were coming up for this new robot that's able to flip burgers, and I guess it's only like $30,000. And you think about, it is replacing an individual to some sense. Hopefully, you can repurpose the individual, but for $30,000, that's a lot of burgers. It seems like a reasonable type of investment. And so you don't really know how that robot works and what it's thinking and how it's viewing everything, but you can definitely see a return on investment on something like that if you're able to deploy it. And so I think as we see more agility and how we're able to approach problems with increased machine learning, increased AI, I think you'll see a greater willingness of adoption as long as it, at the end of the day, as long as it challenges the bottom line.
Right. Any other thoughts?
I think I would like to also add, I think that this is sort of overall trend, right? At least from the software perspective, right? We are moving more and more towards open source, right? And this is one of the, I would believe, an enabler for SMEs to pursue sort of adoption of these tools, right? And build upon their assets, sort of come up with their own innovations on top of their existing stacks.
Yeah, it doesn't have to be really expensive too. I was pleased to see Josh's Raspberry Pis that were on this. You know, you can build a cluster out of Raspberry Pis right now and run some open source software on it. So that idea of being able to innovate, to be able to experiment, that's something we need to figure out how to help small and medium businesses cultivate more as well.
I think that's a great point because even in our experience for the legacy machines like a lathe, we're instrumenting it with Raspberry Pi and then picking up the sensor signals and then trying to do it. I think such things as demonstrated as Paul and Maja were talking about can drive the SMEs into the future.
Yeah, the first supercomputer I built was in 1994, and it's roughly the same power as your cell phone has now. So, you know, what you can build with very inexpensive components and this open source software that you can run with reasonably expensive components, it does foster that kind of evolution that we're looking for.
So
I did find the question. It seems like I missed it a little bit, but okay, I'll go with my answer.
I want to go to the next question because we have about 7 minutes. So obviously this is on everybody's mind. COVID has changed everything. And then in fact, there is a big movement of relying on our own supply chains instead of global supply chains for everything. So obviously SMEs are going to play a big role in this. And what do you think manufacturing is going to be into the future? And then what do you think US should be doing to become self-reliant?
So I think this is a super tough question, but obviously a very important one. Yeah. You know, we've got the pieces in place. I would say that the one thing that we may or may not be missing in the US, depending on how we think about the future post-COVID, is natural resources. So leaving that aside, we've got manufacturing capabilities, we've got logistics, we've got engineering, we've got support networks in place. What we don't have is the glue that sticks these things together. It is not a technology problem. It is a policy problem and a people problem. Interoperability, huge issue, not really addressed that well. Cybersecurity, huge issue, needs to be better addressed than it is today. We don't have perfect solutions, but I can tell you that if you go into a factory and you see the PLCs that are online and you know anything about cybersecurity, you would be absolutely horrified with what is on the network controlling critical infrastructure, right? So if you can figure out how to safely share data, how to deal with those cultural problems of a rising tide raises all boats, you know, and stop the infighting where people cut others down rather than celebrating their successes and try and jump on board with that, then I think we're in a really good place. But we need the right mindset. And that's what we struggle with today. I don't have a good answer for that, other than to say everyone should play nice.
Any other thoughts on this?
Mostly that was, you know, outside of the resources, and I agree with a lot of it is policy challenged in how we approach things. And so then it's kind of a question of, you know, can we remove policy challenges somehow with technology, with data, with better understanding of how things operate, so we're able to bypass some of the policy and improve the knowledge of our system, so we might be able to solve the same problem but with a different path that might not face the same obstacles. And so, you know, maybe there's some opportunities there, but it's definitely, there's definitely a challenge with just, you know, understanding what natural resources you have at your disposal, and also not being able to adjust to everything that gets thrown in your path.
Wonderful. Any additions? So I think we are almost coming to the end. Any final thoughts each one of you want to share? We'll start this time with Maya.
I guess I'm looking forward to the future of manufacturing. I think we are in a very interesting sort of situation, right? There's a lot of opportunities to innovate, right? To innovate how we build and sort of build upon existing manufacturing processes, and how we also bring this sort of this interplay of human and cyber physical together. So that would be my parting thought.
Josh?
Yeah, I think I agree with you. The future is bright. I think we're in an interesting place because people had caught up to technology, and then technology accelerated, and now people are lagging behind. So I'm excited for when people catch up to what's already available today and use it to its fullest. And I think there's just amazing untapped potential waiting for us there.
How about you, Jimmy?
No, thank you so much for inviting me. I certainly always get more out of these kind of environments than I give. The idea of seeing the future and the things that we've been doing actually for a very long time become even more crystallized in the way that we create things. I think that's exactly what's going to keep us going, and I'm really excited about it.
Thank you. Paul?
Yeah, thank you for the invitation and for the participation. And I guess thinking back at it, if you'd asked me what AI and ML were 10 years ago, which I was doing AI and not so much ML, I'd probably give you the same answer 10 years ago as I could. The answer from 10 years ago probably still holds true now. But what they actually are and how they're deployed have completely changed as we've grown, and what our capabilities are, the data that we have, and just how we deploy things. And so be interested and curious to see if that rings true for the next 10 years and what comes up with, they essentially mean the same thing at some level of context, but what are the new things that we can do with it? And what are the new gimmicks or the new capabilities that are going to be introduced in the coming future?
Wonderful. So I think we covered everybody on their final thoughts. I think one important thing that comes through today's discussion of an hour and a half presentations and the Q&A is that the AI is nothing new, or machine learning is nothing new. I think it has been there for a while. As a grad student, I worked with AI. And then as a young faculty member, I did edit a book on AI in manufacturing theory and practice around 1990. How are the problems changed? I wouldn't say they have changed drastically, but the technologies have they changed? Yes. Computing has changed? Yes. But the problems have become more interesting, and real time has become more important. I think that is the theme that runs through this whole discussion. I think all of I think we had a great panel here that is seen by, we had a large audience who stayed almost till the end. And this being lunch hour, maybe perhaps they're eating lunch too, but still, I think that is a good indicator for the strength of the speakers here. I thank you so much. And all the people who are listening to this or watching this, if you need any kind of further clarifications, please feel free to contact me, and then I will relay your questions to the panelists and then coordinate with them. Thank you so much, and be safe wherever you are. And I thank the panelists for taking the time and helping me out and helping the community out. Thank you.
Thank you.
Thank you.
Bye.